Welcome back, students. Let's resume our discussion in section 3, selected topics from number theory. Previously, we studied the division algorithm and its proof. It was long and difficult, but we went through it. Now let's go to the next topic, the greatest common divisor. This theorem consists of two parts. First, the existence, and second, the property. The existence first. Given pair of integers a and b, they exist a certain whole number d or non-negative integer d such that d is a common divisor of a and b. In other words, d divides a and also d divides b. And finally, d can be written as a linear combination, ax plus by form, where x and y are integers. Look at this carefully. The conclusion consists of three parts: green, blue, and red. A whole number, or non-negative integer, that's green, and common divisor, d divides a and d divides b, that's blue. And finally, the linear combination, these ax plus by form, red. So we have to prove all these three, green, blue, red, for a certain non-negative integer d, and we have to prove that thing exists. And that's what we're going to do here. Existence first. And then we're going to consider its properties, because if there's a chance that something does not even exist, then it's totally meaningless to consider any kind of properties or uniqueness or whatever. Existence must be established before anything else. And that's usually the hardest. And that's what we're going to do right now. So, ready? Here we go. It's going to be a long and difficult proof. Step 1, a trivial case, when either a or b is 0, or maybe both are zeros. Without loss of generality, we can assume b is equal to 0. If a is 0 and b is non-zero, then we just rename it and make b is equal to 0. We can always do that without loss of generality, because it's basically a renaming, reordering. And depending upon the sign of a, we can define d as a linear combination like this, or like that. When a is greater than or equal to 0, define d as a times 1 plus b times 0, which is a, and that's a whole number because a is greater than or equal to 0. Now, if a is less than 0, then we define like this: a times negative 1 plus b times 0, so it's negative a, and that's a whole number because a is negative. Consequently, negative a is positive, so it's a whole number. So we have red and green. Either way, red and green. How about blue? Well, b is equal to a, and a divides a, of course. You see, a is 1 times a and d are the same, so d times 1 is a. Consequently, d divides a. And as for the other, well, everything divides 0. Anything times 0 is 0. So we have it, a common divisor. How about this case? D is equal to negative a, and negative a, of course, divides a. Negative 1 times negative a is a, and negative a is equal to d, so negative 1 times d is a, so d divides a. And as for the other, everything divides 0. So yes, we have the common divisor property, blue. And then, from the construction, we get red and green. Okay, so much for the trivial case. So when a is 0 or b is 0, or both are 0, then this is true. Now let's consider some non-trivial cases. First, when both are positive. And this is going to be the main body of the problem. That's the hardest part. And step 3 is not going to be too much, actually. Let's copy and paste this thing right here so that I don't have to scroll that much further up. So basically, that's what we want to prove. And we're going to assume that both a and b are positive integers, 1, 2, 3, 4, and so on. And we're going to use induction on a plus b, which will run from 2, 3, 4, 5, and so on, because both a and b begins from 1, and the smallest possible value is going to be 1 plus 1, which is equal to 2, and that's the base case. After proving the base case, we can set up the inductive hypothesis, and based upon that inductive hypothesis, we'll prove the next, and then that's going to be the end of the proof. Okay, first, the base case. A plus b is equal to 2, which means a and b are both equal to 1. In that case, let's define d through this linear combination, a times 1 plus b times 0, which is 1 times 1 plus 1 times 0, and that's 1. And is that a whole number? Yes, of course. 1 is a whole number. It's greater than or equal to 0. So we have red and green, linear combination, and whole number. Now, do we have blue? Well, d is equal to 1, and 1 divides everything, actually. A, B, D, they're all equal to 1, so 1 divides 1, so B divides A, and also B divides E. Yeah. We have common divisor property, blue. And from the construction, we had red and green as well. So the base case is done. Now let's go to the inductive hypothesis. Suppose that this conclusion is true when a plus b is less than n. And then we are going to prove for a plus b is equal to n. This is a strong induction. The usual induction goes like this. Prove for n and then, assume for n and prove for n plus 1. Or assume for n minus 1 and prove for n. But this is strong induction. We assume for anything less than n, and we're going to prove for a plus b is equal to n. This is going to be hard. But what choice do we have? Let's take it one step at a time. Let's see. The conclusion of this is true. So we have red, green, and blue. So let's see. Red, a linear combination. And green, that's a whole number. And blue, common divisor. D divides A and D divides B. And this is true whenever a plus b is less than n. Okay? Alright, assume that, and then we are going to prove this when a plus b is equal to n. Here we go. Let's assume that a plus b is now equal to n, and then let's make an ingenious observation here. A minus b plus b is less than n. Do you see that? This number, which I'm highlighting in bold, plus b is less than n. Why? Well, a minus b plus b is a. You see, this b and that b cancel out. And that's less than a plus b because b is positive. You see, a and b are both positive integers. And that's equal to n. So we have the sum strictly less than n. Okay, comfortable? All right. So let's take this one as I highlighted in purple right here. Then we can use the inductive hypothesis. First number plus second number is strictly less than n, so the conclusion follows. Except that instead of this a, I have to use a minus b. So that is going to be replaced by a minus b. That's going to be replaced by a minus b. Compare. First number plus second number is less than n. First number plus second number is less than n. First number is a minus b here, a over there. Second number stay the same. So replace the a into a minus b. If you do that, that's what you're going to get. D is this linear combination, as we have over here, and that's a whole number. And then blue, common divisor. Please note that I replaced a by a minus b here, and again a by a minus b here. So that's what I get by applying this inductive hypothesis for these two numbers, a minus b plus b, which is less than n. Okay, all right, we are almost there. We have d, and which is a whole number, and let's manipulate a little bit, just a little bit. Oops, just a little bit. This d, break up parentheses and then factor b out, we have a linear combination of a and b. A times an integer plus b times an integer. So if we wanted this red, we have it. And then it's the same number d, so it's a whole number, of course. So we have green and red. Remember, x is integer, y is integer, so y minus x is integer as well. So it's a times integer plus b times integer. So it's this form. Yes, we have red and green. Now how about blue? Well, we know that d divides b and d divides a minus b. From those two, can you prove that d divides a as well? If so, then we are through. We already have red and green. That's coming directly from the inductive hypothesis, and this will follow if you prove it. That's left to the students as a homework, but as a matter of fact, I have the answer key here. No cheating. It's a homework problem. It's okay. We completed the proof through the strong induction. So this is true when a and b are both positive integers. Now what if one or both of them are negative? No sweat. Use this observation. If a is negative, then ax can be rewritten as negative a times negative x. When b is negative, negative b times negative y. When both are negative, like this, so that we have positive numbers, either negative a, b, or a, negative b, or negative a, negative b. They're positive, depending upon the circumstance. So this part exists, which is whole number. Consequently, yes, we have this linear combination as well. So we have red and green. As for blue, well, d divides a is equivalent to d divides negative a, and same for b. So whether we have negative a or a, what's the difference in terms of dividing? No difference. So we're going to get blue as well. Make sense? This red can be rewritten like this, where negative a is positive and b is positive, even though a is negative. So from here we get this linear combination, and that's the whole number. And then of course for positive or negative a, divisibility by d is equivalent, so the blue property also follows. Conclusion, native case also holds, and finally we have the existence theorem. That concludes the existence part of the greatest common divisor theorem. We are going to come back and discuss the rest of the theorem in a separate video. Stay tuned. See you soon.